Hello everyone. In this video I will be covering the very beginning of complex algebra and I will be introducing the imaginary number. So let's dive right in. Now the reason I began with the reason I plan to begin with the imaginary number is because I feel like it's important to introduce it. So in mathematics the imaginary number is noted by I, which is equal to the square root of negative 1. And this imaginary number has very important applications in various domains that involve mathematics. But in this case, I won't be covering it here. So I think it's also important that I introduce a popular convention in electrical engineering. So I is normally used to describe current, correct? Therefore, in order to avoid confusion between the imaginary number and current, we will instead use j to describe the imaginary number. So now we have j is equal to the square root of negative 1. And to sort of see what ends up happening when we start manipulating j, I'm going to start increasing the powers of j. So you can start seeing what ends up happening to this imaginary number. So let's say we square j. Uh, The way we do this is that we keep the original square root of negative 1 and we square it, as we did with the j. As some of you may know, the square root is really just a type of power, but in this case, instead of being a whole number, it's a fractional value, where it is half. Then we square the entire term, and then using the laws of exponents, we bring in the 2 onto the 1/2, and we end up with negative 1 to the 2 over 2. Which is really just negative 1 to the 1, which is equal to negative 1. And from here we see that j squared is equal to negative 1. Now, from here on out, we're going to start increasing the power one by one so that we see what ends up happening to these j's. So let's move on. And let's begin actually just by rewriting the original j. As we saw before, j squared is equal to negative 1. And now let's examine j cubed. So this can be written as j times j squared, which is really just j times negative 1, since we proved that j squared is equal to negative 1. Therefore, j cubed is just negative j. And the reason that we're increasing the powers one by one is because eventually as the powers increase for j, or the imaginary number, the output will start following a certain pattern depending on what the power is. So now let's move on to the next power. So we have j to the 4, which can be written as j squared times j squared, which is just negative 1 times negative 1, which is a negative times a negative, which means that the answer is just positive 1. Now let's move on to the next power. This right here can be written as j times j to the 4th. From here we see that this is really just j, and j to the 4th is 1, so that means that this is j times 1, which is just equal to j. Now let's move on to j to the 6th, and we'll describe this as j times j to the 5th, which is really just j times j, since j to the 5th is j. And we end up with j squared, which from before we saw that j squared is negative 1. And from here we see that j to the 6 is really just the same answer as j squared, meaning that the value has already been recycled, or in another way of saying it is that the pattern is already starting to begin. So we'll see that when we moved on to j to the 7th power, it'll match the same value as j to the 3rd. And from there, we'll prove it. So this is really just j times j to the 6th, where this is just j times negative 1, which is negative j. And from here we see that it really did follow that pattern as to what would have been j to the 3rd power. And we see that as the powers keep increasing, we will be dealing with a pattern that involves just either negative 1 negative j, positive 1, and positive j. And it'll just keep on cycling between these four different values. So now before we move on completely, we're just going to cover how to solve j to a more to a much higher power. So in this case, we'll pick j to the 39. Now, the way I like to do it, it may not be the most efficient method, but I usually like to group up the imaginary numbers in terms of a power of 2. So therefore, I will be dividing 39 by 2. In this case, we get 1 here, bring down the 19, just basic division, and we end up with a remainder of 1. Now, the reason that this is important is because the remainder tells me whether there's going to be a singular j left over from the entire simplification process. I'll show you what I mean by that in a bit. While the quotient tells me how many j's squared there will be. So what I mean is that j to the 39 is really just a singular j, which is from the remainder, times a bunch of j's squared multiplied with each other, where the total number of j's squared is equal to 19. And the reason that this is important is because we first noted that j squared is equal to negative 1, and 19 is an odd number. Therefore, meaning that in this whole term here, we're just multiplying a bunch of negative 1s with each other. And because the number is odd, the entire result of these j's squared being multiplied with each other is really just negative 1. So therefore, j to the 39, and I will actually write that up here, is really just j times negative 1, meaning that j to the 39 is negative j. And from here, we can prove it by actually plugging in this little term into our calculator. So j to the 39 is really just negative j. And now we proved that there is a method of simplifying j when it has a certain high power. And we see that it follows the trend that we noticed earlier as we kept increasing the powers. And well, I think this is important. We might not be dealing with such high powers in our equations, but it is a good method of understanding how to simplify j, the imaginary number, when it has a certain power. And that'll be it for this video. In the next video, we will be covering or introducing Euler's formula or Euler's equation, and then from there moving on to what a rectangular form or a polar form is of a certain function or equation. And that'll be it for this video. All right, until next time.